Hello, this is Dr. Joe Trout from the physics program at Stockton University. Today we're going to talk about work and energy and power. So when we talk about work, we talk about force through a distance. So in most general terms, it's the force multiplied by the distance that the force is applied. So in this example, there's a 100 Newton force and it's moved for 20 meters. So the work that's done is 100 newtons times 20 meters, or 2,000 Newton meters. We use the unit Newton meters a lot for work and energy. So we defined a unit called a joule, and 1 joule is equal to 1 Newton meter. So in this case, the work that was done was 2,000 joules. We also use foot-pounds in the English units. So here we have 40 pounds of force applied to the box, and it's drugged 10 feet. In this case, we have 40 pounds times 10 feet, or 400 foot-pounds. Power is the rate at doing work. So power is the work divided by time. So for example, if we have applied 100 newtons for 20 meters, and it took us 2 seconds to get there, then we find that our work is 100 newtons times 20 meters, or 2,000 joules. And the power is the work divided by time, which is 2,000 joules divided by 2 seconds, or 1,000 joules per second. And 1 joule per second will define to be a watt. So 1 watt equals 1 joule per second. So for example, you might have a lamp in your kitchen that has a 100-watt light bulb, and it puts out 100 joules of heat and light every second. Another unit that's used is the horsepower. The horsepower is 550 foot-pounds per second, and it's equal to 745.7 watts. You may notice that if we plot the force versus the distance, the area under the curve is equal to the work. So in this case, the force is constant. So the force times our displacement, which we'll call S, is equal to the work. So if we want to find the work, we can plot the force versus displacement and take the area under the curve, and that will give us the work. So for example, if we apply 100 newtons and we travel 20 meters, then the work is the area under this curve, which is 100 newtons times 20 meters, or 2,000 joules. So let's say you get a really bad summer job, and your job is to move boxes from point A to point B. So how many boxes can you move in 40 hours? So let's say on your best day, you can apply 200 newtons of force. And each one of the boxes weighs 1,000 kilograms. So we see that we'll drag the box 20 meters, and we have 200 newtons. So each box, the work will be 2,000 joules. So how many can we do in 40 hours? Well, we have our acceleration will be the force divided by the mass. So our acceleration is 0.2 meters per second squared. And the distance we're going to travel is 20 meters. So we have x equals v naught x t plus 1/2 the acceleration in the x direction times time squared. And let's say we start from x naught equals 0 and our velocity is 0. And we drag the box across the floor. So we find out the time is equal to 2 times delta x divided by the acceleration. So this will be 2 times 20 meters divided by 0.2 meters per second squared, or about 14.14 seconds. So let's say we skip lunch and we don't count the time that it takes us to walk back and get another box. Then we have 40 hours, and we'll convert the hours into seconds and divide it by the time it takes us to drag one box across. And we get about 10,000 boxes. And let's say you get paid by how many boxes you move. So the first week, you're really happy. You've moved about 10,000 boxes and you have a big paycheck. But your back hurts. And you realize, hey, you know what? If I don't bend over all the time, my back won't hurt. So let's say instead of pulling 200 newtons this way, you attach a little string to it or a rope, and so you don't have to bend over all the time, and you still apply the same 200 newtons. And let's say your rope makes an angle of 60 degrees with the horizontal. And let's do the same analysis. Only this time, don't forget, the amount of force that's actually being used to move from A to B is 200 newtons times the cosine of 60. So some of your force is being used to lift up the box. But that's not what you're getting paid for. You're getting paid to pull the box from A to B. So what we see is that if I look at our acceleration now, we get 200 newtons times the cosine of 60 divided by 1,000. We end up with 0.1 meters per second squared. And we'll do the same analysis and find the time. So we get the square root of 2 times 20, but this time divided by 0.1 meters per second squared. And we find out that it takes us 20 seconds to move a box. And we take our 40 hours, convert it into seconds, divide it by 20 seconds. We've only moved 7,000 boxes this time. And our paycheck is small and we're really unhappy. But you can see what happened, right? All of the force wasn't going into moving the box. All of the force wasn't going into doing the work. Some of it was lifting the box up, which is perfectly okay, but it doesn't get the box from point A to point B. So what we really need is the amount of force that's moving in the direction of our motion. So something is not consistent. So only part of the force really does any work moving from from point A to point B. And this is the component of force that is parallel to the direction of motion. In this case, it's F times the cosine of phi. And we're using this angle, we're calling this angle phi in this chapter. So what we really should say is we want the force dotted to the displacement, or the magnitude of the force times the magnitude of the displacement. By the way, this time S, the displacement, is just in the X direction. So we replaced it with delta X times the cosine of the angle between them. Or really what we're saying is we want the component of the force that's parallel to our direction of motion. So we want the component of the force that points in the direction we're moving. By the way, the net work is equal to the sum of all the works. So here we only had, we were only considered the force that we applied. So what we'll say from now on is that the work is equal to the dot product of F's, the force, dotted to S, the displacement, which is equal to the magnitude of F, the magnitude of S, times the cosine of the angle between them. Don't forget the dot product is a scalar product, so work has no direction. However, work can be positive or negative. Work can help you move from one place to another, and there's forces that can hinder your movement. So let's take this example. Here we have a box, and we're pulling the box from A to B. And we're going to apply 100 newtons at an angle of 30 degrees. And there's some friction about coefficient of friction of kinetic, and let's make the kinetic equal to the static of about 0.1. So we draw out our force diagram, we see here's the force, and we find out that the normal force will be equal to the weight, 196 newtons, minus how much we're pulling up, which is 100 newtons times the sine of 30 degrees, which is 146 newtons. So our normal force is 146 newtons. And our force of friction is mu times the normal force. That's 0.1 times 146 newtons is 14.6 newtons. By the way, we're calling the force of friction, we're just using a lowercase f to save a little bit of room. So let's find the work done by each force. First, we have the work applied, the force applied. So we have 100 newtons times 10 meters times the angle between our displacement, which is along the x direction, and our force, which is 30 degrees. And we end up with 866.03 joules. Then we will look at the work done by the force of friction. Well, we said the force of friction was 14.6 newtons, and our displacement is 10 meters. But what's the angle between our displacement and the friction? In this case, it's not 30 degrees. Our angle between the displacement and friction is 180 degrees. So what we end up with is 114 newtons times 10 meters times the cosine of 180 degrees, which gives us negative 146 joules. So work can be negative. Work done by a force can also be zero. So let's look at the normal force. Here we have the normal force times the displacement times the cosine of the angle between the normal force and the displacement, which is 90 degrees. But the cosine of 90 degrees is zero. So the normal force doesn't do any work. This shouldn't be really surprising because the normal force is not going to help you get the box from point A to point B. What about the weight? The work done by the weight will also be zero. In this case, it's 196 newtons times 10 meters times the cosine of negative 90 degrees, which is 0 degrees. So we see part of our applied force does some work, the part that points in the direction of motion. The friction does negative work. It's trying to hinder our motion. The normal force does no work, and the weight does no work. So if we add all these up, we get 866.03 joules minus 146 joules is 720.03 joules. Not forgetting that the weight and the normal force do no work, and the friction does negative work. So let's carry this a step forward. Let's say that the work is equal to the net force times delta x. Because the net force will be moving in the direction of motion. But the net force, according to Newton's second law, is the mass times the acceleration. Let's assume that the acceleration is constant. Well, if the acceleration is constant, we have v final squared minus v initial squared plus 2a delta x. Note that we went back to using final and initial instead of naught being for time equals 0. I'll explain why soon, but for now, just realize that we're using final and initial instead of the value and V naught, or V and V naught. From there, we can solve for our acceleration. And in fact, let's solve for acceleration times delta x, because we're going to plug into this equation. And we get V final squared minus V initial squared over 2. And I'm going to plug that in for A delta x. When I do that, I end up with the mass times the velocity final squared minus the velocity initial squared over 2. And we're going to call this value 1/2 the velocity time the mass times the velocity squared, the kinetic energy. So we're going to define a term called the kinetic energy. And sometimes we use an uppercase K and sometimes we use an uppercase KE. And we'll define it to be 1/2 mv squared. So now we find out that the work is equal to the kinetic energy final minus the kinetic energy initial, which is equal to the change in kinetic energy. So kinetic energy is energy due to motion. And kinetic energy, we're going to be defined to be 1/2 mv squared. And if we apply work to some object, we find out that it's equal to the change in kinetic energy. The net work is. So for example, let's see what happens here. We're going to apply a force of 100 newtons over 30 meters. So the work that's done is the force times delta x, which in this case is 3,000 joules. So the work we get is 100 newtons times 30 meters, or 3,000 joules. And let's say we start with an initial velocity equal to 0. We can use that to find the final velocity. So the final velocity will just be equal to the square root of twice the work that was done divided by the mass. So we get the square root of 2 times 3,000 divided by the mass, which is 30 kilograms, and we end up with 14.14 meters per second. Now, we didn't have to use work and energy to do this. We could have used forces, but this is a second way of doing the problem. And somewhat times it's a better way. By the way, we don't have to consider just constant acceleration. So if we look for the change in work, it'll be equal to the force times dx. And let's go ahead and integrate both sides from x initial to x final. Sorry, this should be an x initial to x final. And it's the mass times the acceleration for the force times dx. But the acceleration is dv dt. And the velocity is dx dt. So we end up with the integral of, from v initial to v final, of the mass times v times dv. And if we integrate, don't forget the mass is constant, if we integrate v dv, we just get 1/2 v squared. So if we plug in for the final velocity, we get 1/2 the mass times the velocity final squared, minus 1/2 the mass times the velocity initial squared, which is the kinetic energy final minus the kinetic energy initial, which equals the change in kinetic energy. If we don't have a constant force, we have a varying force, what we do is just break up our force into little chunks of force, right? And take them over a small area, and we can figure out, right, this is just the integral under the curve. So if we have a varying force, we can just take the integral under the curve and we find out what the work is. This is easy if it's a constant force. We end up with the force times, right, the force comes out of the integral sign, and we end up with the force and the integral of dx, but the integral of dx is just x. So if the force is constant, we end up with f of x, x minus x final minus x initial. If we have a spring, we said that the spring was equal to kx. Really, you said minus kx, but let's put it as the magnitude in there for a minute. And if we look at the integral, k is just the spring constant. So if we integrate x dx, we come up with 1/2 kx squared. We'll find out that this is the energy stored in a spring. By the way, if we look at power, we could write it as dw dt, which is equal to the force times dx dt. So if the force is constant, then the power is just the force times the velocity. You'll need that in physics too, so that's really important. So the power is equal to the force times the velocity, if the force is constant. So let's end there and we'll take it up on Monday.